So recently, the National Ambient Energy Building Research Symposium took place. And if you missed it, we want to share with you what was learned and really ultimately how we can naturally heat and cool our buildings with no to minimal mechanical systems. This NAEBRS group, will also reconvene as part of the American Solar Engineering Society in 2026 at one of their conferences to really help keep this momentum going. So please join us here today and see what we have learned. Now, before we get started, if you want to talk about our mechanical systems, especially for these ambient type buildings, the reality is having what we call the magic box, right? The magic black box, as you might name it. And so Build Equinox, our sponsor with the Serve 2 and the Serve 1000 for commercial projects, make a ventilation system, but this ventilation system also has a heat pump integrated right into it. And it's very low load. But if you can imagine, if we can achieve ambient energy with our buildings, their type of system might be in really good place to be that magic system that heats, cools, ventilates, takes care of humidity issues as well. So whether you have an ambient building, passive house, or just are building more sustainable and better, go check out Serve for advanced smart indoor air quality systems, and thanks for their support. All right, so welcome to what we learned about ambient buildings that heat by nature at the NAEBRS conference. This session is brought to you by the GreenHome Institute. The GreenHome Institute is a nonprofit with a mission to empower people to make healthier and more sustainable choices in the renovation and construction of the places we live. We are a small but mighty team of two, and today I will be your moderator. My name is Brett Little, and I am the education manager here. This course is approved for multiple continuing education units, including 4 pillars under our Certified Green Home Professional designation: health, energy, materials, and place. AIA Health, Welfare, and Safety may make it applicable to your state-based design or contractor license. Check out our 5-digit Passive House code if you're not at the Passive House conference right now and need your CEUs. That will be sent to you, as well as a huge thanks to Energy Smart Institute, who is helping us get our courses also approved for the International Code Council, ICC. Check out Energy Smart Institute for all of your Raider trainings. So with that, I'm going to actually hand it off first to Debbie, who is our longtime board member, our vice president, and oversees our education efforts and committee. And she'll help introduce herself and the rest of our speakers. So Debbie, glad to have you back on. Welcome and take it away.
Okay, thanks so much, Brett. Thanks everybody for joining us today. Brett, it's always my pleasure to help GHI with the weekly educational webinars that you've had consistently for years. So our speakers, briefly, I'm going to introduce them. Keith Sharp, professional engineer, will go first. He'll be followed by Mark Challam, a delightful architect. And following Mark will actually be myself for a slight little case study overview of other architects. And then last but not least, Julian Wong, professor of architecture engineering, will be doing a lot of wrap up. And then we will come back with Keith at the end to do a where do we go from here kind of approach. And one last thank you to everyone who has made a donation to make this webinar possible. So that being said, thank you, and take it away, Keith.
The NAEBRS conference was held in Ghost Ranch, New Mexico, and you can see the website there. Eventually, we'll have all the presentations there so you can go and see them whenever you'd like. The organizing committee is listed there, and you'll notice 4 of us are speaking today, but also want to recognize Brian Robinson, who was a key part of getting the funding and organizing the conference and actually executing it at Ghost Ranch. So first, I just want to briefly say, what is ambient energy? It is that free energy from the sun, air, ground, and sky. And passive solar heating is probably the most recognizable application. And we have had a number of presentations on passive solar heating at the conference. Direct gain is the easiest, and there were lots of examples of that. Nighttime ventilation cooling is a way that we can cool without having a mechanical system. Ground loop cooling and heating is another application. Earth-burned buildings are another example. We can also cool from the sky. And what is shown here is Harold Hayes' original prototype from 1967. But during the symposium, we had a number of examples of sky cooling as well. So why is ambient energy important? We have known for a very long time that fossil fuel increases atmospheric carbon dioxide, which increases global temperature and causes more severe storms and a number of other problems. But more recently, we have found out that 20% of human deaths can be traced to air pollution by fossil fuels. So we need to get rid of fossil fuels as soon as possible. Why is ambient energy important in buildings? It's because almost half of our energy is used in buildings. And that includes pretty much all of the residential and commercial sectors, a part of the industrial sector, and there are a few buildings in the transportation sector like bus stops and airports. So buildings must be addressed in order to meet our long-term sustainability goals. In buildings in the residential and commercial sectors, we use fossil fuels directly for the gray and black parts of these columns, but the blue bars are electricity, and currently that's 60% fossil fuels. So every time you flip on a switch, you are burning fossil fuels in most areas around the country. But aren't we transitioning away from fossil fuels? Well, actually, it turns out we are not. By 2050, if we have low economic growth and low zero carbon technology costs, we may decrease fossil fuel use for electricity by 14%, just 14%. On the other hand, if we have high economic growth and high zero carbon technology costs, we will increase fossil fuels for electricity by 35%. So we are not on track. And it's important to recognize that electrifying buildings does not mean that they are decarbonized, as long as they're using electricity. So solar buildings are already doing some very positive things. Back around 1990, there were several estimates of the number of passive solar buildings, up to about 300,000. And now the count that we have is by the American Housing Survey, and the question that's asked is the fuel used most for heating. And likely, that's that tan curve there, likely that rise represents photovoltaics, and we're not counting passive solar very well. So we don't have a really good count. But if we just take 300,000 buildings and assume that 50% of that is for space conditioning and we're doing 50% of the load, that comes out to 4 average size power plants. So we are already offsetting a lot of that fossil fuel by using the sun for space conditioning. But there's also a lot of potential because 300,000 is still a pretty small number compared to the total number of buildings, 140 million residential buildings and 6 million commercial buildings. So ambient conditioning compared to doing conditioning with renewable electricity, where we would have wind turbines and solar panels and all the conversion steps and storage and transmission and heat pumps, is simpler. And that should look pretty obvious by just comparing these two figures. Just allowing the sun in and storing the heat in thermal mass is so simple. It's also cheaper because of the simplicity and the fewer materials. It's lower carbon. Concrete, which we think of as a high carbon material, is actually 10 times lower carbon than batteries. It's also more resilient. There are lots of failure modes in our electric utility, and the passive solar building is so simple and much more resilient. It also promotes health by giving us a connection with nature. So we had a number of presentations at the conference on the history of passive solar, and I want to turn it over to Mark Challam to talk about that history.
Okay. Anybody see my slides? Because we got a lot to look at here. Can we get rid of the box here? Okay, can you see the full slide?
Yes.
Yep.
Okay. Well, I'm going to quickly go through a couple of thousand years history here in New Mexico of our applications of passive solar architecture. This is my presentation, so I hope it doesn't get cherry picked. Let's go back to the history of New Mexico with the native peoples and native cultures here in New Mexico. Their architecture was quite sophisticated. They did cliff dwellings, multiple family housing, no insulation, so your neighbor was your insulation. Many of these examples all over New Mexico and Colorado. Acoma Pueblo, built with solar lights. One row of building, do not shade the other row of buildings during the winter solstice, the lowest sun. The stair step concept from the low south to the upper is very, very common, creating a wonderful flow of thermal warm air to heat people as they work on these terraces. Taos Pueblo is a really good example of that. Also, Acoma. Pueblo Bonito in Chaco Canyon is one of my favorite buildings. It's 5 stories tall. Again, it stair steps from the lower south to 5 stories upper, creating these warm little areas for people to work. Very, very sophisticated. There's a lot of archaeoastronomy that is part of this complex. Anna so far with the Solstice Project has done a lot of research in Chaco Canyon and discovered the Sun Dagger, which is an archaeological calendar showing not only major, the 4 cycles of the sun, but also the 18.5-year cycle of the moon. Very, very sophisticated, very exciting project. One thing New Mexico really had going for it, not just the amount of 300 days of sun a year, but the adobe construction. We already had thermal mass. Thermal mass was not surprising to us. We had a lot of wonderful architects, teachers, Paul McHenry, Bill Lumpkins, to name a few of the great architects, John Gamim, working with Adobe design and construction. Mel Medina had the best mechanized system in New Mexico with his laydown machine. He could make 20,000 Adobes a day. Quentin Wilson, an instructor at Northern New Mexico College, taught Adobe construction, various methods of using earth and Adobe for roof constructions with vaults, arches, and domes. Joe Tibbetts was another hero of mine. He wrote the Earth Builders Encyclopedia, which is the whole Earth catalog of earth and construction. Joe also did a whole lot of classes in Adobe construction. He also produced the Adobe News magazine and in Inter-America Adobe Builder magazine, which came out, and we all waited carefully at the mailbox waiting for our issues of Adobe News. It's just an incredible way of tying the Earth community together, and very effective. Let It Shine. John Perlin wrote the 6,000-year story of solar energy. When it came to the 1970s, early 80s, scientists were debating whether to use air collectors or thermal fluid collectors. Well, we were just doing it here in New Mexico with mud and sticks. It was happening. We were doing it. Our concept was the building was the machine. Utilize the building and the natural effects of the sun and wind on these structures to heat and cool them. That was very, very effective. One of our great leaders, Peter Van Dresser, was a radical economist, environmentalist. Here he is sitting with Hassan Fadi, the famous architect from Egypt, who did the mosques up in Abiquiu. Peter was an incredible author, thinker. Some of his books, Development on Human Scale, Landscaping for Humans, and Homegrown Sun Dwellings on the Sun Dwellings projects. Very famous books and very helpful. Another great leader we had very early on was Steve Baer. He was an incredible thinker, planner, activist. This is his zone house. Oops, wrong way here. Steve was an incredible mathematician. He developed the zone balls, zone design, and these little balls were actually used by scientists to develop models of DNA. So Steve was an incredible mathematician. He was an author. He wrote Sunspots and More Sunspots. This photo I really love. It's from that great $5 book, Whole Earth Catalog. Steve continued to stay with solar energy up until the end. This is 2022, when ACES came to Albuquerque, and I introduced Steve to Carly from ACES. A very exciting moment for all of us. Bill Lumpkins, definitely our hero, designed his first solar adobe home in 1935. He was the one responsible for the Balcom House, which was published in books and magazines all over the world. Bill also wrote some beautiful books, Pueblo Architecture and Modern Adobe, and Casa del Sol, which is passive solar home designs. A really, really great book. I helped Bill with that. Another great person that we had in New Mexico that really helped us was Doug Balcom. He gave us the engineering, he gave us the tools. He studied passive architecture, mathematically analyzed them, and gave us the guidelines for builders and many, many other articles and tools for analyzing and predicting performance of passive solar homes. At this point, we were no longer lunatics. Again, Doug in Los Alamos did a lot of testing on Adobes and different systems. Again, you saw the Doug Balcom House. It was called that because Doug moved into it. It was actually designed by William Lumpkins, Susan and Wayne Nichols, who did a number of wonderful passive solar developments here in Santa Fe. David Wright, another great passive architect, started here. He was an apprentice to Bill Lumpkins. When he went out on his own, I took David's chair in Bill's office. But David designed beautiful passive solar homes utilizing Adobe. This is one of his famous ones, Sundown, which was built by a dear friend, Karen Terry. There's a picture of Karen and some of her houses, some of her work. Her mud plaster was just beautiful. One thing I say is Karen put the soul in solar architecture and gave it beauty, which really gave it national attention. Bill Yonda, another one of my great friends, was the Johnny Appleseed of passive solar greenhouses. This is his book is being republished. There's little Katie. Little Katie has teenage sons now and daughters. There's Bill and Susan Yonda with the two little kids. They were building these solar greenhouses all over the country for about $2.50 a square foot. Ed Mazzaria, another homeboy. He's the one who called the architects to it and said, guys, We're the ones that are using all the energy, and we really need to do something about it, and we can do something about it. Ed wrote the book, the Passive Solar Energy book, which made understanding passive solar design much easier for the general public. It's really well drawn and explained. Another great person, engineer from Los Alamos, Bruce Hunt, designed this wonderful two-story tram wall, did a lot of monitoring, testing, analyzing, and shared all his information and performance with us, which helped us, again, develop more information on tram walls and the ability to design better. Ben Lutz, president of NMSEA for a number of years. He's a physicist. He started up in Los Alamos. He's worked with many of the great scientists up there, and he wrote these passive solar design guidelines for northern New Mexico. Everybody needs to take a look at those. It's a fantastic document, again, a wonderful tool. Thank you, Ben. Carlos Viceps, an architect from Taos, also very active in designing passive solar homes. He also designed and built the Sun Trailer, which is what NMSEA, the New Mexico Solar Energy Association, used to travel to different schools and different events to explain how solar energy worked from all kinds of ways. Another wonderful hero, Bruce Davis, designed a number of passive solar homes. He worked with Karen Terry a whole lot in designing her homes, and Bruce is a real hero. Lives in a double play home, worked with Steve Bear. Scott Morris, engineer, scientist, river rafter, was very interested in natural convective loops and did many um, thermal siphon air systems downslope. This is one of his famous ones. This is the solar hot air balloon from the Ghost Ranch, launched 1 year out of a solar conference. He started with a big thermal tube that would go down the mesa, and that was used to inflate the balloon. The balloon was designed to keep itself hot and inflated. It went 300 miles over the Sangre de Cristo Mountains and landed somewhere in Oklahoma. Adobe Solar Associates, Quentin Wilson, Bill Yonda, and myself went on the road in New Mexico and Arizona, teaching the concepts of Adobe construction integrated with passive solar design. Bristol Stickney, a wonderful engineer, has been very heavily involved. He was the Energy 10 master here in New Mexico. Bristol loves taking energy from one source and putting it into another. He also worked with me on night sky radiant cooling, and we did a wonderful 2-summer testing facility, came up with all kinds of conclusions and formulas for utilizing night sky radiant cooling, which is extremely effective here in New Mexico and many other parts of the country. Another interesting architect here in New Mexico was Mike Reynolds, who designed and developed the Earthship. You know, if we could do it with mud, he could do it with trash. So he did a wonderful job developing art. You know, his homes were art, very carefully crafted, using tires, using bottles, using cans as his fill in his earth and cement structures. Beautiful structures, wonderful community up in Taos. Myself, I've been involved since the early 70s in designing and building passive solar homes for myself and my family. My wife Betty and I and son Matthew have built 4 homes together, lived in 3, and we're still married. This is our house here in Santa Fe. It's a wonderful house. We have a 2-story greenhouse, which I'm sitting in now, which heats and helps cool the house. This is our little getaway up in Abiquiu. It's 750 square feet with 850 square feet of finished out garage, and it's a wonderful retreat for us. Our work has been published in various magazines. I'm really happy to have two covers with Solar Today from the American Solar Energy Society, and I've been written up in many magazines and books. We live rather sustainably. We play with all different technologies. Here we have 3 different solar ovens that we've been playing with. Of course, a solar clothes dryer, and here is a solar food dehydrator that we built a number of years ago and utilized. Ghost Ranch and the Life Techniques Conference. Peter Van Dresser, Steve Bear, Keith Haggard developed the first solar conference at Ghost Ranch in 1972, and we've been meeting ever since. It's been a fantastic education. In 72, there were no books to learn from, so we taught each other. It was a wonderful collection of people. We went year after year after year up at Ghost Ranch. We became brothers and sisters, and very, very exciting time. We also published the Sun paper and the Southwest Bulletin from NMSEA. It came out monthly. The amount of information that was shared in these publications is quite extensive from all different aspects and angles, and it's mostly passive, very low-tech concepts. At the Ghost Ranch Conference, we had many speakers, many great speakers from out of the state, like Jeff Cook, professor of architecture from ASU. We've had Harold Hay come out. We've had Amy Lovins. We've had Pliny Fisk. So we had quite a collection of people that would come join us and share. It was quite an amazing time and quite an education. We then turned to outreach, where instead of going up to Ghost Ranch and teaching each other, we decided to be outreach, went to Albuquerque and invited the public to come join us and see how we utilized solar energy in various ways. A lot of the solar companies set up their little booths, and we had a great time sharing with the general public. We have our big solar ovens, we had little solar ovens, we had very many examples of solar energy. ZoneWorks and Steve would come and set up. Quentin would come down with Adobe and set up. Here in 2022 at ACES in Albuquerque, we honored NMSEA. Here are some of the presidents of NMSEA that still exist. I could name this many people that are not with us anymore that were wonderful people. We still get together, we still gather. We do need to wear disguises because of Trump. So we're very careful of how we meet and where we meet. The Sun Dwellings, a very important project here in New Mexico. This was done in 1976 up until about 79. This was a project developed by Peter Van Dresser, spearheaded. Keith Haggard came in and helped out. Aubrey Owens from Ghost Ranch helped out. But the idea was to design 4 simple Adobe test buildings and monitor and see from wall compared to direct gain, compared to a greenhouse, compared to a what we call a control non-real solar building. But the south wall, being Adobe uninsulated, still gave us a fair amount of gain. We had natural ventilation built in, as well as thermal siphon water collectors. Ghost Ranch gave us a site up there at Ghost Ranch where we could build the 4 buildings. And there they are, the greenhouse, trom wall, direct gain, and the control unit. The Sun Dwellings design team was a very incredible group of engineers, scientists, architects. Peter Van Dresser, for sure, was the leader of the group, organized. Then we had Francis Westling, UNM mechanical engineer, Bill Lumpkins, architect, and main architectural leader. Nan Nalder was a young architect working with us. Buck Rogers was a fantastic engineer. I've never met anybody who could figure out things in his head just by looking up to the sky and coming out with an answer in 10 seconds. Aubrey Owen was our Ghost Ranch liaison, really helped with funding and bringing in money. Here, Keith Haggard was first president of NMSEA, was part of the staff, did a lot of the administrative work. Then there was young David Wright, architect on the team. And then, of course, me, I was the gopher for the whole team and did everything I could do to help out. On site, we had Ray McCall, Peter Van Dresser, myself, Ramon Dominguez, who worked the construction aspects, help. Shirley, we got enough money for a secretary, so we had a nice smiley face in the office. And then again, there was Quentin Wilson, the Adobe construction manager. Quentin and I really kind of controlled the whole thing. I taught the passive solar aspects to everyone. Quentin taught Adobe construction. I taught Quentin, Quentin taught me. We had 20 young students from northern New Mexico, the Hispanic villages, and the local pueblos. We were able to live at the ranch. We were fed, we were housed, and we were paid. No other program like that in the country since. It really, really was successful. The first half of the day, we were in classroom learning from contractors, plumbers, engineers on the aspects of construction. We learned structures. We had some lessons in mathematics. Second half of the day was out in the field working on the buildings. So it was half and half. Quentin and I developed a book. There were no textbooks back in those days, so we did our own textbooks. Since those guys didn't read, we drew the textbook. It was all pretty much just drawings and figures. We've used it in many, many different workshops. Here we are on site gathering stone, stone. We made our own adobes. We went up into the mountains and we cut our own timbers for these structural beams. We peeled them by hand with draw knives. We made our own adobes. We learned how to lay adobes, mixed our own mud, just natural mud from the field there, and started building. Insulation was sawdust in the roof and pumice in the north wall and perimeter of the building. We just laid raw pumice and then set flagstone into a mud floor. We made our own doors. We made our own windows. We've had a lot of articles done on us as we were building and then after the construction. These are the most high-tech, low-tech buildings in the world. We work with Los Alamos Labs in setting thermocouples all over the buildings, in the floors, inside, outside, in the ceilings. This is a scan through a trom wall, so we can actually see the heat wave moving through the wall. Los Alamos was extremely helpful in developing this. 50 years later, we're still looking at the ramifications of this program, still very important and still valid. We're very proud to be part of it. Sooner or later, the state even got into it and started publishing source books on solar energy. This is the back cover, and what's exciting, you don't see a collector in there. It's all passive, and most of the book was all passive and really well done. Well, the story continues. We have the National Ambient Energy for Buildings Research Symposium recently up at the Ghost Ranch. It was extremely successful. People from all over the country came, shared, met, became friends, and it was rather successful. We hope it'll continue. We had tours, we had lectures, we had poster sessions, and we're very proud of the group that we had. So it could go on and on. There are people that I have not mentioned. I've pretty much just talked about the people that I have worked with and I know intimately, but there are so many more that need to be talked about, honored, and documented. So I want to thank you for the time, and I turn it back over to Keith or Debbie.
Coleman. I'm an architect with Sun Plans, and I specialize in passive solar residential. As Brett said, I'm on the GHI board and the education committee. I'm also chair of the American Solar Energy Society Solar Building Division. I'm going to share my screen and will basically cover just a few other presentations that were also presented at Ghost Ranch. We had over 50 presentations there. I'm going to do some case studies. I have about 9 of other architects. Can everybody see my screen okay?
Yep.
Okay, super. Okay, so jumping right in, Mark already talked about Karen Terry houses. Well, let's just see, backing up. Here's just some overview of some pictures. And I'm having trouble advancing here. So this is an overview of the 9 presentation, the case studies that I'm going to go over today. Karen Terry, Mark already mentioned her and Bruce Davis had a unique relationship, design build, where they created passive solar homes with very unique features. Many were bermed on the north, so they benefited from the stable earth temperatures there. In cross section, you can see that they incorporated the clear stories to bring light and solar gain into the middle of the home. Interior thermal mass was a combination of adobe, concrete, stone, often integrated into the hearths, and the interiors were a creative mix of unique ceiling configurations and natural light. Okay, so jumping to something a little bit more recently, although this starts with the 1980s farmhouse. This was one of my favorite presentations at the NAEBRS symposium. This is by Andy McDonald, the homeowner. This was a major renovation with net zero energy goals or better. So they added extensive insulation. They exposed the brick wall on the interior for thermal mass, which was a very warm feeling, and created a sunroom on the exterior so that both sides of this lovely brick wall were designed in as a feature. On the exterior, they had vines that would grow thick in summer, provided seasonal shade for the south and the west glass. And they reused a lot of materials, minimized waste, designed in water conserving features. And then lastly, they had a small array of solar panels that provided the remaining energy required in the form of electricity. The solar art barn on Martha's Vineyard. This presentation was by Mark Rosenbaum, professional engineer with Energy Smiths. He was the mechanical engineer on a very unique structure that was designed and built by South Mountain Company with Matt Coffey as the architect. So this structure was approximately 2/3 gallery and 1/3 workshop. Plus, they had a 3-season greenhouse that was about roughly 15% of the total enclosed area. The total enclosed was maybe 2,900 square feet. So this unconditioned greenhouse was designed by Mark to have a minimum temperature of about 50 degrees. To do this, he designed in a blower that carried the excess daytime heat from the greenhouse into the basement below that was full of 5-gallon water storage containers. So this system can be summarized as one with active storage with a passive release. The Helios Spitti home, GHI has a whole webinar on this particular house by Jim Riggins, the homeowner, retired HERS Raider and also retired fighter pilot. Jim had passive house priorities with adaptations that he made to a Sun Plans design as a starting point. The design incorporated direct gain with south glass of around 8% of the floor area. The primary thermal mass was in the concrete slab. Overhangs shaded the south windows in summer. And these walls were double stud, I believe about R49, and the roof trusses contains R67. Both of those interior structures, assemblies had a thin layer of foam for condensation reasons. Below slab, they had R23. The south glazing, I believe, was not as high as some of the newer windows, but still pretty good, a U of about 0.22. And the solar heat gain coefficient for the south glass was as high as possible that could be purchased at the time, about 0.60 for the glass alone. That's usually not the rating for the whole window. And the air leakage for the whole house was around 0.40 air changes per hour at 50 pascals. Jim said that about a cord of wood has been used for heating over the past 10 years that they've been in the house. And their single 12,000 BTU mini split has been occasionally used for cooling. In addition, he has a deep earth tube that preheats the air for the ERV unit. His garage unit is a custom-made passive solar air heater on the south side of the garage that passively heats this unconditioned part of the home. Okay, moving on to Amanda Bramble's presentation, the continued relevancy of low-tech passive solar. Her learning center is the Ampersand Sustainable Learning Center, and she's sort of a New Mexico DIY instructor, and her presentation was very inspiring as she shared the variety of simple, sustainable DIY type of strategies that they've integrated into their off-grid homestead and demonstration site. There's a lot of affordable, low-tech solutions, including using recycled windows for direct passive solar gain, construction of a solar oven on the south side of the home, water collection systems that also included passive solar water heating and batch collectors, reuse of conventional water heaters painted black for simple outdoor hot showers. So basically, their learning center teaches how to harvest the renewable resources of sun, gravity, rain, and dirt. An experimental mid-century Adobe townhome complex, La Luz de Oeste Foundation. This was presented by Pat Gallagher, mechanical engineer. This 56-year-old Adobe cluster housing complex is now on the Registry of Historic Places. So the complex has adobe walls on 3 sides, the north, east, and west, and brick floors for the thermal mass, large windows of glass on the south side, overhangs calculated to shade those windows in summer. And those windows also provide a great connection to nature that's so important with the wide open land. Passive house to zero energy. This was a very interesting presentation by Joachim Karcher, an architect with Zero E Design. Very good passive house principles overview he presented, and he showed how he put the principles to use in 2 of his passive house designs where the free solar gains are heating the home. The first home, the Adobe one, Chamisa Passive House in Taos, is a certified passive house, LEED Platinum, site net zero energy. The windows are just under 6% of the south windows are just under 6% of the 1,800 square foot home. The heating load is about 8,000 BTUs. That's easily met by solar gain most of the time with the thermal mass inside that helps store the heat. He also had a very interesting new project, Dolan Street, which showcases all electric living with prefab construction, where most of the construction of the components takes place indoors. And the insulated walls and roof panels are then lifted into place. So these 1,000 square foot units have a 12,000 BTU heat pump. They have 3.25 kW of PV on the roof, and their average construction cost was around $270 a square foot. The average utility bills, he told us, are about $58 a month, and that includes charging 2 electric cars. Okay, direct gain homes. These were by design builder Steve Cowell of Colorado. He had examples of direct gain components, which is basically the south glass, overhangs, and thermal mass. Again, very simple. I really like this photo that he shows of the one house with the summer solstice and that same photo at the winter solstice, where you can see the full sun in winter and the full shade in summer. So Steve's interiors include simple thermal mass materials, again, of concrete slabs and stone hearths. He also integrates a lot of passive cooling components, which really is a part of any well-designed passive structure. And in addition to the overhangs that were calculated for south windows on his west facade, he minimizes the use of glass and maximizes shade on that west wall. He places windows as much as possible high and low for a stack effect with cooling. Windows on the opposite sides of room for cross ventilation. That also helps with reduced glare when you have balanced light. Integrating ceiling fans, which can make spaces feel about 4 degrees Fahrenheit cooler, and attic fans to maximize nighttime cooling when the climate allows. Making Place for Change. This was by Victor Olgier, FAIA. Victor's an architect with Green Design Collaborative. Victor's Well, let's see. Sorry about that. Victor's presentation emphasized the importance of comfort as being essential in building design. And he says, by eliminating discomfort, we create conditions that allow people to realize their full potential. In his presentation, Victor traced the pioneering designs of Hungarian-born architects in the mid-20th century with their principles for bioclimatic and sustainable architecture. The Olgier's 1963 publication, Design with Climate, synthesized their scientific, architectural, and humanistic thinking into a holistic framework for climate responsive design. So as wildfires, rising temperatures, and ecological instability intensify, the Olgier's vision to remove the environmental load from the human shoulders and empower architecture as a force for human and planetary well-being is more relevant. By providing comfort, we can make place for positive change. Thank you, Victor, for that inspiration. And last but not least, we're showing the roof pond buildings. This presentation was by Alfredo Fernandez, an ACES fellow and award winner. He's professor of architecture and the director of the Natural Energies Advanced Technologies Laboratory at the University of Nevada, Las Vegas. Alfredo discussed the roof pond system that was conceived by Harold Hay. It's an indirect gain strategy for passive solar heating that also provides passive cooling. The California house shown on this slide achieved 100% heating and cooling by this method. Alfredo's research conducted at Ball State University in Indiana and the University of Nevada, Las Vegas, it demonstrates the viability of roof ponds in various climates. And not full case studies, but just very briefly, I'd like to call out a few other presentations that were covered at the conference. Simple tool for identifying passive solar gain. This is actually my own poster. I'm developing a tool that'll be useful for existing homes that have passive solar features to identify that, and for homeowners that are building new homes that will not be modeled in more complex software. A new era in education for homeowners, Christina Ransberry. She has a Resilient by Design consulting program that helps landowners design and build their naturally efficient home using ambient energy. John Barrows talked about climate responsive design in the home building industry. This was very insightful. He's a longtime NHB member, has been involved with their teaching, and he recently has introduced the ambient energy concepts to NAHB subcommittees. So that was very good to hear. Revive 2024, this is a resilient focused building retrofit standard that's being developed by CEUS. And Al Mitchell talked a little bit about that and the resilient requirements, where buildings must be able to maintain safe indoor conditions during a power outage for a week. And I think that's both in winter and summer. A biophilic approach to net positive architectural design education. Mary Guzowski, professor of architecture at University of Minnesota and author of several books, including Biophilic Net Positive Design, was a wonderful inspiration at the conference. Enrico Bonalori with Emu Passive did a presentation, Cornerstone of Thermal Comfort of High Performance Windows. Lisa Moret with Colorado Earth talked about thermal mass and phase change materials. Lauren Rochelle, Center for Maximum Potential Building Systems, covered a 3D printed agri-hood model, which was very insightful. And I could go on and on. There's passive solar physics, solar cats, changing hearts, solar cookers, night sky radiation, hydroponics, crop protection, and bringing ambient energy into the home building industry, which I'm very excited about. So that concludes my case study. And now I'm going to turn the presentation over to Julian Wong. Thank you for your attention.
All right, thanks, Debbie. All right. Okay. All right. Hi, everyone. My name is Julian. I'm a professor in architecture engineering from Penn State University. All right, I'm going to share my screen. Oops. Okay, just hold on a second. Yeah. So, yeah, just a brief about myself. My background is architecture engineering. Actually, my initial career plan was also architect with the focus of sustainable design. But I keep studying in the research direction now. Become a researcher in the building technology, building physics area. So I'm currently in Penn State, teaching courses in both architecture engineering and architecture. My part of the presentation will just focus on some of the passive technologies and their current status showcased at the conference, especially those that connect the passive design, some advanced materials, and data techniques in the system of buildings. So what really stood out at this year's conference to me, so I learned a lot because I see it's kind of the historical land with many pioneers in the system of design and also passive design projects. But we also see a lot of innovations is happening at both ends of this kind of land, the spectrum, from very simple passive and physics-based solution like radiant cooling or some thermal mass material to a little bit more emerging like data techniques, simulation techniques, modeling techniques to optimize building performance. So this is the one example. I think Mark and Debbie also show some examples about that. So we do have a few presentations, particularly focusing on the method to harness energy from the sky. This could be tracked to some really old, ancient structure, which is a kind of a passive refrigerator. I think the term I learned is yaktro. But fundamentally, this can be transferred to the current technologies with the basic thermal radiation principle. So one of the interesting talk was by Bristol Stickney, a solar thermal engineer. So he demonstrated how flat plate solar thermal panels are actually operating in reverse at night, radiating heat out to the night sky for cooling. He also showed integrated design using same hydronic loops for both solar heating and nighttime cooling. So case studies like the two I just showed from here, Los Alamos Eco Station and the Sandian Mountain Natural Historical Center. So really show some energy savings and also the water use savings. So the takeaway here is sometimes low-tech and reversible systems can be incredibly effective if designed integratively. So that theme of blending art, science, and also geometry continued in Paul Hildebrandt's presentation on the Zoom 2 Cool Sky work. So which connected early experimental structures by Steve Baer and also the Zoom works to today's bioclimatic design thinking. So another highlight is relatively new or emerging materials is from Professor Xiulin Ruan at Purdue University. So his team developed ultra white paint that can reflect 98.1% solar radiation, including both visible and infrared, which is much more than typical white light, commercial available white light. So they can reflect a lot of the visible and infrared. Meanwhile, it has very high emissivity. So then they can emit the heat efficiently to the space, also utilizing the sky condition, the cool sky condition. So they integrated some nanotechnologies, especially nanoscale features, structures into the material development. This allow them to design this kind of material to even have passive cooling during the daytime, no electricity needed. So just the painting rooftop and or facade could lower surface temperature by a few degrees by several degrees compared with the typical white paints, commercially available white paints. So they noted that covering 1% of Earth's surface could theoretically offset global warming trends. So it's a low cost, lightweight, and applies like regular paints. So really expected, looking forward what kind of final products could be coming from the university from there. It's also focusing on material, but in the phase change part or thermal mass direction at NRail, Sanjit and Paulo introduced a new metric I think they call that thermal C rate. So thermal C rate to evaluate how fast phase change material charge, discharge, store, and release heat. So we know phase change materials are well known for potential energy saving, especially the peak demand reduction. But it's also challenging to evaluate performance from the long-term perspective and the operation perspective. That's what they're trying to address. So using this new metric, their studies have found the ceiling integrated PCMs have the best charge and discharge behavior than wall-based. So what's important here is they give us a quantitative benchmark to compare different PCM systems and how to integrate them into more predictable simulations or energy goals. On the other hand, the conference also has a few presentations talking about the data-driven intelligence, machine learning, AI, combined computational simulations, or advanced technologies, how we design and retrofit building for comfort, resilience, and decarbonization. The first one is from I. Mitchell. He is a building scientist in CEUS, presented CEUS Revive framework that integrates energy modeling, resilience metrics, and also climate risks analytics to guide decision-making about the retrofit at a scale. So it's not just about energy saving anymore. It's about keeping homes safe during outages, during heat stress, quantifying climate mitigation risks, and also automating the life cycle cost analysis through simulation. So the framework seems more comprehensive and cover a lot of parts about sustainability. So it seems a lot of potential, especially for design and potential retrofits at the early stage to support decision making. The last one is I just want to share our own research work at Penn State. Is also in this track about the data-driven or data techniques. So the reason we work in this area is because of some conversation we had with our local nonprofit organization. They're from Philadelphia, actually. So they have a lot of work working with home repairs, retrofits, and weathering programs for low-income communities. But they also face, because they face a large number, so here you could see some numbers over there. They face large numbers about low-income homes, but they have very limited budget and resources. So how to screen and select those most vulnerable homes from the current stock, and then make audits, repair, it's important to them, but it has been challenging. They have to have a lot of person, very laborious, and a survey, a lot of phone calls to eventually make the decision, but they're still not sure whether they make the good selection. So our project is sponsored by National Science Foundation and also Housing Urban Development, trying to develop a new method, kind of a fair metric that removes the effect of home size, the weather issues, just focusing on building envelope and the building system efficiency. So using that metric, we can see the inefficient homes are really caused by the window or the roof or the infiltration, just using some simple surveyable data. So that's something we have to adopt machine learning and AI techniques into, just using surveyable data from each homeowner, such as a home area, age, home story, story numbers, like wall types, roof types. And most of it just descriptive. And our expectation, we can use this model to predict that kind of scale. So that scale will give to the decision makers, those nonprofit organizations. They will know which homes from their stock they are most vulnerable compared with the average home. So they will make their selection and do the deeper analysis. Yeah. So just one summary. So what we see emerging is kind of a convergence from two directions. We do see a lot of the fundamental, very passive and simple physics-based solutions like passive design, from architecture, from thermal materials. But meanwhile, we also see a direction from the conference, some new techniques from simulation modeling or data or AI. They can be used to put them together. We can design the building to be more adaptive, passive, and also regenerative, right? Using both Asian principles and cutting edge methods to shape sustainable environments. Yeah, that's all. Thank you. So I think now we put back to Keith. Yeah.
So here at the end of this presentation, we want to answer the question, where do we go from here? Well, maybe not entirely answer it, but one idea that I have is that it would be great to have a design tool that is accessible to architects and homeowners, and even to engineers who don't do building simulation for a living. So I have a simple program for simulating buildings that are completely ambient conditioned, that is based on thermodynamic similitude and the energy balance that has just the 5 main components: 2 gains, solar heat gain and internal heat gain, and then envelope loss in the wintertime and ventilation or sky cooling in the summer, and then thermal mass for to moderate temperature swings. So the Buckingham Pi theorem says that we can convert those 5 primitive variables to 2 similitude variables. Pi 1 is the 2 gains over the 2 losses, and then pi 2 is thermal capacitance over the envelope loss, which is a thermal time constant. But for our purposes, we can break pi 1 into parts that represent the solar load ratio, the internal heat to load ratio, and the ventilation or sky cooling to load ratio. And I'll show you why those are important. First, pi 1 equals 1 is an energy balance, but it simplifies even more. During the heating season, we wouldn't be using ventilation or sky cooling, so ILR plus SLR is equal to 1. That's about as simple as you can get. During the cooling season, we would exclude the solar gains, so ILR minus VLR equals 1 is an energy balance. And then sometimes we can't get an energy balance. That depends on the weather. And then we need a time constant that is at least as long as the most challenging period of imbalance. And we're going to show you how that works. So this is the input sheet for my free heat program. And this is for pre-design. This is before we have even chosen a floor plan for the house. We're doing it for Albuquerque because the symposium was in New Mexico. For the first parameter, for envelope losses, we're going to use the passive house limit of 10 watts per square meter. That number is calculated for us, and we just simply transfer it into the green cell. We're going to use the passive house default for heat generation inside. We're going to use the high value of light to heavy conventional construction, since passive solar heating typically needs a little more thermal mass. And then we're just going to use the defaults for solar aperture and for ventilation cooling. There's some optional inputs that I won't talk about that are related to your south-facing aperture and the comfort limits that you would like. And that pre-design is a little bit cool in January, and it's cool, or rather warm for a longer period in July and a little bit in August. So we need to do a little bit of something to meet the chosen temperature limits here. And that's where the similitude parameters come in. We said that SLR plus ILR equals 1 is an energy balance. And there's that line that represents the energy balance. You see that we have 1 week, the first week of January, we don't have enough heat. And so that's why it's getting cool. For a time constant, there are 7 consecutive cloudy days. And so our time constant needs to be at least as long as that. And you can see that it's pretty marginal. And so because it's hard to get more solar gains when it's cloudy outside, changing the time constant probably makes more sense for this building. Before we go back and change anything, let's look at the cooling season. We have 4 consecutive weeks where the cooling potential, the blue bar, is less than the cooling needs, the red bar. So we need to increase the ventilation cooling. We'll go back to the input sheet and we'll increase the thermal mass, and we'll increase the ventilation cooling. And these numbers are a result of some iterations that I'm skipping over, but that makes the house comfortable. We are above the lower comfort limit in January. We're below the upper comfort limit in July. You can change those limits if those don't suit your indoor comfort limits. But we now have a pre-design that we can use and follow when we move along to actually designing the floor plan of the house. The similitude parameters, SLR and ILR, have not changed, but we did substantially increase the time constant. So that helped in the heating season. And then we have increased the cooling capacity to meet the cooling load there during those 4 challenging weeks. This is something that can be done in every climate in the US. And the similitude parameters help us decide how we could change our design to make it fully ambient conditions. So at this point, we'd like to open it up, I think maybe first to the panelists, if they have some ideas about what we could do to promote ambient energy in buildings, and also open it up for questions.
Oh, there we go. Hey, everyone. Yeah, before we get into those questions, just a real quick reminder that yes, this session is being recorded and we will have it posted shortly. So in the next week at the latest, you can check back here on our YouTube channel link, or you can go there right now, click subscribe, hit the notification bell, and you'll get an instant update when it is available. And then also as a reminder, for those of you watching this session in the future, not right now, but on demand, take your quiz with an 80% passing rate to receive your CEUs. For those of you here today, check your spam from certs at gutenbergcerts.com. You'll receive your Con Ed certificate there. You can log into your account and access it as long as you've been here the entire CEU approved hour. And as always, a huge thanks to our board of directors, our volunteers, our executive director, Jose Reyna, our nearly 500 members. We're trying to get to 500 in celebration of our 25th year anniversary this year by the end of the year. So if you haven't signed up as a member yet, get on that, please, and support us. And a huge thanks to our sponsors who are essentially making products that are going to help us achieve some of these results, or at least help us achieve more sustainable decarbonization outcomes, like our top tier platinum sponsor, Ream, for decarbonizing our water heating system. So I wanted to quick, because I know, Julian, you have to you have a shorter time here, so I wanted to make sure I had a couple questions come by thrown your way real quick here, and then I want to get to that bigger picture question you had, Keith. So the first one was on this white roof kind of application, right? And I remember back to a talk we had a few years ago with Joe the Stieberg, building science master. No free lunch, right? There's never a free thermodynamic lunch. You do one thing that you hope helps you, and you might get a a negative trade-off, right? And so one thing I learned from him during that talk, among many things that stood out to me, was yes, the white roof, and this is going to your typical shingled white roof, right, with the low or high SRI. I get them mixed up in my head, but whichever one is more reflective. And the trade-off being, especially in our more humid climates that are colder, maybe a little more humid, is you take away the drying capacity of the roof, where that could cause moisture and durability failures. So you have that, you have that reflectivity, but you have that other issue. So would what you'd be talking about more be, again, targeting these drier climates, or does this new technology approach resolve that moisture issue? Have you thought about that at all?
Right. So from what we learned over there, I think they also make some considerations. I remember they also present some hydrophobic, right? So the one they can resist the high, give the high angle, contact angle to easily release the moisture from the surface. They have not, discussed anything about the moisture transfer, but they do consider the condensation occurred on the surface. They consider another type of layer can make more resistant to the moisture, and condensation water can be easily removed.
Mm-hmm. And so, and then the other question was going to your items about PCMs. And I wanted to make sure I understood or heard you right in that. Were you making a suggestion that the thermal mass? People say we're going to use thermal mass. Well, what does that mean? It's hard to measure. It's hard to understand it. Were you saying that this is a better, effective way to make that more measurable? Did I hear that correctly?
Yeah, so in my understanding, so for when we do the energy simulation or something, we could easily put a thermal heat capacity there, no matter concrete or any material we can put there to do. But phase changing material, they have changeable thermal condition and a different temperature. Um, and I know in Energy Plus, we could also do those kind of things, different temperature, different heat capacity. We could also do that. I think they are proposing something more more user friendly. It's not exactly for detail, structure, the temperature, thermal capacity. It's for thermal storage rate, like how quick about the charge and the discharge. So that rate is specifically they proposed, and they already use that in their large scale simulation to see is that fast charge, fast discharge is good for some materials. So I think they move that forward one step from that perspective. It's not only just the heat capacity, and they bring a little bit dynamic information into the simulation capability. Yeah, that's a really good question.
Yeah, thank you. And Mark, this question came up really early, and you presented, all these wonderful books and resources. So somebody was like, where do I find all these? And I was wondering, I'll expand on that question. Is there a passive solar library someone can contact and borrow these things that it's shared? I mean, obviously someone could go to, you know, Amazon maybe and find all this, but than that, is there a place where people can find these resources and maybe support a passive solar agency?
Not that I know of. NMSEA pretty much gave away their library and most of their books. They do have some information. I know they have a pretty good collection of the Sun papers, which is good. I had a wonderful discussion with Bruce Davis yesterday about what do we do with all libraries? And, between the two of us, we have a pretty extensive library of books, and we're not sure what to do with them. So we're open for suggestions.
Yeah, maybe we put a borrow, and share kind of opportunity or something. But um, yeah, good to hear that. So and just we have the handout. So if anyone's like, what books were you referencing? It's in the slide handouts. I think the other question somebody had asked was all these resources you all were talking about, was there a spreadsheet somewhere we could put them all together, maybe after this webinar, and share it out, the books, the individuals, whatever it might be, like just something that someone could keep it well organized, like, oh, I need to get this resource. So maybe we can discuss that, after the session and put that out later. But speaking of spreadsheets, Keith, the question just came up here about the tool you were going through. Of course, someone's looking at that saying, hey, I'm designing a new or maybe doing a major retrofit. How do I access that and use that? And I'll add to that question, is there someone who provides additional consultations to help make sure they're on track, with their design?
Yeah, good question. And it's something I wish we had the solution to already. But something I didn't talk about is that appropriate weather data has to be
Right.
developed for each
Yep.
location. You can't use just typical meteorological year weather data. It leaves, or it can leave, the house uncomfortable potentially every year out of the 26 years that the National Solar Radiation Database has archived weather data for. So that's something that we need to address, and getting a way to have it available to the public is the big problem. Christina Ransberry, who was at the symposium, is collaborating with me, and we've had a few clients who were close to saying, okay, let's do a design for my climate. But Christina is someone that you could talk with. If you have a design for a new house or a remodel and you're thinking about going all ambient conditioning, then contact her. We're working together.
Yeah, and maybe we can get her on the show to walk through the specifics. And I remember, now that you said it. I'm glad you brought up that climate data, because I remember that back from our last conversation. And and interestingly enough, I just saw an email come out the other day from one of our energy modeling agencies who said that their data they rely on from NOAA is currently being, suspended due to the current shutdown as of this recording. I hope whoever goes to watch this recording, and they're like, what shutdown? There's no shutdowns. I hope that comes up soon, but that's where we're at. So I assume that is going to slow that effort down even more. So if somebody said, hey, I've been tracking weather data in my neighborhood with temperature sensors, and I have, all this data for my community, would that be something good enough to build on a site just to start them off?
Well, it's interesting. Maria Telkis, back in 1948, found 65 years of weather data for her house in Dover, Massachusetts, and just manually looked through all of the weather data and found the longest period of consecutive cloudy weather and sized the storage for her system based on that. That was before we had computer simulations of buildings. And so, it's possible to do that. But the ambient meteorological year weather data is actually a lot more convenient to use.
Mhm. Mhm. And then I guess someone else is adding, like, to expand on this lack of climate data. What if someone wanted to use these concepts or that tool outside of the United States? Is there any other barrier, or is it still just getting this data?
Yeah, so the procedure works internationally.
Yeah.
At least so far, we still have the National Solar Radiation Database, and that's not just for the US. It's for most of the world. And what you do is you take the longest archive years of data that are available, and you simulate the building for every one of those years. You find the most challenging years, both in the summer and the winter, and then you cut out those seasons and then put them together. And that is essentially the ambient meteorological year weather data. And so that can be done if someone wanted to design a house in a place where we haven't developed the AMY weather data, then so far, at least, we can access that data through the National Solar Radiation Database and develop the data for their location.
Now that, at least to me, it immediately sounds like a lot of effort. Certainly, imagine someone who's doing this would be okay with that level of effort if this is what they wanted to accomplish. But I recall, Julian mentioning artificial intelligence, and I think he was mentioning it in the reference of the existing home improvement modeling. But I wonder, could AI also service where you feed the machine, here's all this solar data, and here's where we're at. Tell me what it is, so I don't have to comb through all of this. Is that something that's being explored?
Well, actually, it's easier than that.
Okay.
You could just develop a program,
Yeah.
but it does have to interface with the database. It has to run all the simulations. It has to identify the years and then put that data together. Uh, that's certainly possible without having to use AI. It's just a matter of having someone with the programming skills to get all that done. Right now, I do it just myself, and it takes about a full day or maybe a little longer to get an
Right.
AMY data set. But someone who knew how to access all that data could develop a program that would do that essentially in seconds.
Sure, sure. Yeah, interesting. Well, hopefully that answers some of the questions about access to that. But I guess, yeah, Debbie.
Well, I was just going to clarify the key. So it sounds like you're available as a consultant on a case-by-case basis at this point. Is that right? To any architect and or homeowner that would like to use that tool, and then they would pay you the fee to consult with this on this tool and run it on their home?
Yes, that is the case.
Okay, all right, yeah, thanks. That's great to know. Thank you.
So, Mark, I know you, or sorry, Keith, you had mentioned, oh, wait. So yeah, the next question. Well, I guess we want to keep talking about data here. So the next question that came in, and I had this on my mind too, was, climate change, changing of the weather. You're talking about analyzing past data, but of course we know that's all going to be thrown out the window. Here I am. It's, early October, and we've got a massive heat wave in Michigan. We've been in the average of 70s, and so my energy bills are way down because I'd normally be heating right now. So, I mean, how do you factor in the future in what you're planning?
Yeah, so I mean, that's a really good question. How do you predict future weather data? You really should be designing a house for the weather that it's going to experience, not for
Yeah.
past weather. So there are a number of ways for extrapolating weather data into the future, and it's not clear which method is the best for simulating ambient condition buildings. I mean, in the end, we won't really know until we actually experience that weather. But that research needs to be done to
Hmm.
decide which way is the best to predict weather in the future, specifically for ambient condition buildings.
Hmm. Hmm. Yeah, Debbie, go ahead.
Yeah, yeah, I can't help but just kind of thinking of questions that audiences might have. You have the passive house, which has wonderful standards, and then a lot of people have trouble meeting it, not because of the standards, but because there's no builder that's willing to build it in their little
Yeah.
rural area. So there's the group that's okay, let's do a pretty good house kind of philosophy. It makes me wonder if that same philosophy could be used toward Keith's tool. It's like, okay, we
Yeah.
realize the limitations. We know we're not going to have the most current, broadest weather data, but
Yeah.
can the client, which is the ultimate person who makes a decision, says, okay, I understand the limitations. Can we do a pretty good calculation
Yeah.
and accept at that level, with the main goal being to get this usable by a lot more people.
Yeah, so the comfort limits that I've used so far in my simulations are just hard lines, and we're not allowing the house to get below a certain temperature, not allowing it to get above a certain temperature. But in a conventional building, if you have a power outage and it's more than several hours when the weather's bad outside, you're going to have either hot or cold temperature inside your house, even though you think that your heat pump or furnace or whatever is going to keep the temperature right at exactly the temperature you like the most. So
Hmm.
it may not be as realistic to have to stay within those comfort limits. I mean,
Hmm.
passive house allows the temperature to be higher than 25 C for 10% of the year. That's actually a lot of hours. And if we use that more lenient guideline, then just in the example I showed, the pre-design with just those initial guesses for performance parameters might be just fine.
Hmm.
And yeah, and then on the other hand, some people want it to be between 72 and 73, and they won't accept
Yeah.
anything else. So it
Well,
does depend on the client.
yeah. And that reminds me of the kind of question that came in before this session about, you know, the question is sort of about sizing their heating and load calculations for these types of homes. Obviously, the idea is that you don't have those, but if you start thinking about future climate scenarios where you have an extreme weather event and you want to have a backup system in place, right? How would you properly size a system for that. And this is the same question we give to the standard traditional manual J heating size people, right? You're sizing the system on the past. Well, what is the future when you're sizing your system? And so we bug them for that too, right? In fairness, that's kind of a question for them as well. But how does that play into this conversation where you might be saying, hey, here's your ambient house based on the past, but we know that you might have an extreme event. And so here's your fail-safe system designed to keep you safe, right? What would that look like? What would that conversation look like for HVAC, I guess, in your system?
Need to go down there and do it.
Yeah, so yeah, I've had that conversation with more than one builder about they don't want to dive into the deep end of the pool and go without any backup heating and cooling.
Right.
And it's hard to argue with that, especially if it's the first house that you're giving this idea a shot with. And it's like Jim Riggins. He put in a mini split, and then, if I remember correctly, he turned it on 4 times in 5 years. So it's there and kind of as a security blanket. But then if you don't use it, well, maybe the next time you build a house, you just don't spend the money for it because the performance is going to be good regardless.
Mm-hmm. Well, maybe there's a question here. I guess at a high level, someone was asking comparison of your tool approach. And maybe I'll open this question up to everyone here about everyone's design approach. And of course, how it now is comparing to what I would say is our gold standard, which is the passive house tools. And of course, there's 2 passive house tools. There's Woofy, and I think Woofy's going away, and there's a new one. And then there's passive house planning package. So the first question is, how do those 2 compare to each other? But let's just say you lump them all the same. You have the sort of passive house tools, right? So how is this different at a high level compared to what we're talking about here?
Yeah, so Freeheat is a dynamic simulation, and Woofy Plus is also a dynamic simulation. I've used both, and they give essentially the same answers.
Okay.
But PHP is a static calculation. I wouldn't even call it a simulation. It's monthly calculations. It does not incorporate thermal mass the way it needs to be incorporated to catch those hourly temperature swings. So it is not a tool that should be used to design an ambient condition building. Woofy Plus, that's great.
Any other thoughts, Debbie, just from your perspective on passive solar design versus passive house?
I think with the manual J being, or heat loss, heat gain, load calculation being part of the building code, assuming the building code is followed, it sort of leaves us being designers, homeowners, kind of at the mercy of that tool, which the consultants that I've worked with have consistently said that residential manual J level does not take into account passive solar design. So if that's the case, I usually strongly recommend that clients work with mechanical, not really an engineer, but a designer that understands passive solar and is willing to make subjective, well, I guess you could say they're objective if they make changes, but to be able to understand that systems are routinely oversized in that category and explain that effectively to the homeowner. So really kind of coordinating with the building inspectors and builders and just awareness that that is a limitation or that they might run into it. I mean, I know there's some codes that or some inspectors that are not requiring it, but just to be aware that it exists and that could be a limitation on any design system.
Yeah. Mark, I want to, I guess, bring you in for the last thought, and that is, looking back at the past, we have all of these beautiful ideas and thoughts and the people who put into it in this prescriptive approach of how it's been done. But of course, everyone's kind of asking these questions around, okay, like what are the ways we kind of know that it's going to be effective and work? And I'm just curious from your perspective on what you're seeing from the past to where we're headed, where people need that higher level of certainty, if that makes sense.
Well, I'm getting pretty excited about all these modeling programs that are out there. It just gives us the validity, gives us the tool to be able to compare the new house to the one we have just finished.
Mhm.
And we're able to develop our own little library of homes and how they perform. And with these tools, we can compare the new homes to the older homes that we have designed and continue to improve on the performance.
Yeah, Debbie,
Yeah.
and I think let's give you the last thought and then wrap up.
Right, I know we're getting ready to wrap
Yeah.
up, but I just wanted to comment on a comment I saw in the chat from Drew where he was talking about the minimum size of systems. And I know a lot of times we'll have a client and they will want, you know, we're anticipating their home to be 100% heated and cooled, but to meet code, they still have to put in at least the heating system. So the
Yeah.
simplest, least expensive system is often what happens. Whether it be electric baseboard, as inefficient as that is on a theory
Yeah.
standpoint, or small propane heater, as much as that can be controversial in the natural gas. But Keith also mentioned a pipe heater. So anyway, inspectors will often be open-minded and look at other minimum heating systems. The mini split heat pump, what I love about it is that it also provides the cooling. So just to concentrate on minimum sizing.
Yeah. Yeah. Well, and someone made a great observation too that, oftentimes we get pulled into these small solutions, the heat pumps, ventilation systems, whatever it might be, but that this, ambient is a systems thinking, a larger conversation, thinking through all the aspects versus let's just attach this one mechanical solution and solve it all. So I appreciate that comment and that observation. And I think that hopefully, sums up everything we talked about. So, so yeah, with that, I want to wrap this session up with the time we're at right now. I guess, I think I'll reach out to you all to kind of put that sort of resource list together so we can send that out too ahead of time to kind of figure that out. But I guess from there, where can people go, since this is about the NAEBRS conference? I'll just say, where can people go to learn more about what the next gathering will be for that momentum that's being built?
I could make a plug for the American Solar Energy Society and the solar, because we have a solar buildings division. So anyone that joins that, and some of the membership levels are really low, can then join the solar building division, where Julian and I will post comments on updates with neighbors, type of events and other solar building events as well.
Yeah.
That's ASES, ASES.org.
Great. All right.
Might add,
Go ahead, Mark.
I might add that this conference was very important. There was a lot of information presented, and I'm really glad that ASIS is looking to pick up on it and help us continue sharing this information.
Yeah. Yeah. Big thanks to them. So go check that out. And I know we want to keep this conversation going too. So I'm sure we'll have some more thoughts coming your way as well. So thank you all for joining us and staying on a little bit longer. I appreciate all the comments and feedback, and we will catch you all next week for another session for GHI webinar. So take care. Goodbye.
Hey,
Thanks,
thanks
Brett.
so much, Brett. Thanks
Thank
everybody
you.
for your time today.
Be sure to check out all of our courses available online that you can watch anytime and anywhere to pick up your CEUs. Before you go, make sure to subscribe to us on YouTube to get weekly updates and stay up to date on green building science courses, webinars, and home tours. Thanks again.